Most machine learning models we've looked at are trained using calculus and gradient descent. But what if I told you we can build a classifier without either of them? No gradients, no iterative optimization, just statistics. And despite making one ridiculously naive assumption, it can work surprisingly well. This is Gaussian Naive Bayes, and in this video we're going to derive exactly how it works. Imagine we have some data x and our job is to classify into one of the k possible classes. How could we do that? Well, here's one way of thinking about it. Suppose we could somehow calculate the probability that this data belongs to each class. If we had those probabilities, classification would actually be pretty simple. We could just choose the class with the highest probability. So mathematically we write y hat is equal to the arg k max p y equals k given x. So in other words, out of all of our possible classes, which one is most likely to give the highest value of k given our dataset x? But here's a problem. How do we actually calculate the probability of y equals k given x? Y equals given x using Bayes' theorem. Now we can make our lives a little easier. Remember, we're not actually interested in the exact probability yet. We're interested in which class gives us the highest probability. And notice that the probability of x doesn't depend on k. Our data x stays the same while we're comparing the different classes. So the p of x is the same for every class. Dividing every score by the same number isn't going to change which one is the largest. So we can ignore it, which means that the probability of y equals k given x is proportional to the probability of y equals k multiplied that by the probability of x given that y equals k. Now this algorithm works by making a pretty big assumption. It assumes that once we know the class, each of our features is independent of the others. This is called conditional independence. So instead of having to calculate this, we can split it up into this. Or more compactly, something like this. And this is where the naive in naive Bayes comes from. Because in the real world, assuming all of our features are conditionally independent is pretty naive. Features can be related to each other. For example, being interested in AI and being subscribed to this channel probably aren't completely unrelated. And if you happen to be one of these people, please like, share and subscribe. It helps us at Confused Robot make better math videos for a wider audience. Anyways, we've dealt with the naive part of the Gaussian Naive Bayes. We still need to calculate each of these. And that's where the Gaussian part comes in. We're going to assume that each feature within each class can be modeled using a Gaussian distribution. In other words, a bell-shaped curve. And each one of these curves is determined by two things. Its mean, which determines where the curve is centered, and its variance, which determines how spread out the curve is. So imagine we have a table containing our training data. For every class and for every feature, we can calculate its own mean and variance. So this is where we were before. And using our independence assumption, we can convert the probability of x given y is equal to k as a product of the probabilities. And since each feature within each class is modeled as a Gaussian distribution, we can substitute the Gaussian equation over here. And the probability of y is equal to k is simply the proportion of our training data belonging to class k, so we can substitute that as well. And mathematically we're done. However, computationally we have a problem. When numbers between 0 and 1 get multiplied, the product becomes smaller and smaller and closer to 0. And we call this a numerical underflow error. To solve this, we can take the log of this entire thing, and this simplifies down a few things. Firstly, since the log of AB is equal to the log of A plus the log of B, the product becomes a sum. So if we apply our log laws, we get something that looks like this. Oh, and by the way, this method doesn't affect which class k is chosen, as the logarithm is an increasing function. So whichever class had the largest original score also had the largest log score. And that's how we can train a model without gradient descent.